Okay, so now we're on the difference between temperature and temperature change. So this goes on to tell us what a delta T is. So I want to reinforce this a little bit, that delta T, anytime I refer to delta T, I will draw it like with a triangle and a T. That stands for delta T. And now this is the temperature difference or the temperature change. For example, if I had a substance that was at minus 15 degrees Fahrenheit and I went up to 40 degrees Fahrenheit, what is the delta T between these two numbers?
55.
That's right. It's a 55-degree delta T. It's the temperature change between these two. As you can see, we have to go through zero. So we're adding these together. So it's the temperature difference between the two numbers is considered to be delta T. And we're going to work with this just a little bit more when we start talking about sensible heat.
It's just the temperature difference, Doug?
That's all it is. That is correct. Thank you. Yeah. Now we give a little table here on nice to know temperatures. Body temperature in Celsius is 37 or 98.6. Everybody's usually pretty close to that. Now, room temperature, it says here 70 degrees or 21.11 degrees C. In my house, this is probably 24 degrees C. My wife likes the house hot. So I keep turning down the thermostat and she doesn't know it. Because I have a little app on my phone to turn down the thermostat. She goes, how come it's cold in here? I'm like, oh, maybe you should put on a sweater. You know, that usually helps. So that way it's nice and cool for me. Anyways, hot water setting, a typical normal domestic, this is domestic hot water, is usually set for 140 degrees Fahrenheit. Does anybody know why we want 40 degrees Fahrenheit? 140?
So you don't burn yourself?
Okay, there is a scalding part to this. Now,
It's to prevent Legionnaire's disease, isn't it?
That's correct. So there is a scalding thing also associated with this. We have in every single residential application, a bathtub now has to have an anti-scald or a temperaturely controlled or positive temperature controlled shower valve, right? Tub and shower. It is now, I think, code that you have to have this. So this is a mixing valve that is really what is in your shower these days. So and cut it down. The 140 degrees Fahrenheit, if that temperature is maintained at that, then everything is fine. But as soon as you go below 140, so if you say you had 120 degrees Fahrenheit and you had that water sitting for a long time, you can create bacteria in there. And that bacteria sometimes is Legionnaires. I'm not spelling this correctly. That should be an N. Legionnaire's disease. Anyways, I'm looking at the chat. I'm not sure what that means, but that's okay. So that's why we have hot water tank settings at about 140 degrees or higher, typically not too much higher than that, because then you can get into problems of scalding and overheating, etc. Normal boiler temperatures is about 180 degrees. and max temperature for a low pressure steam system boiler is 250 degrees at 15 psi of steam. So those are nice to know temperatures. And that brings us to this little objective 1 exercise, which you can do on your own time. And
Hey,
it's
Doug,
continued there. Yeah,
how hot would you say scalding temperatures of water are?
I'd say about 140 degrees. Yeah, so that's why in tub and shower valves, we have a mixing valve with, it is a mixing valve, but it's a positive temperature control. So it doesn't get above, I think it's 89 degrees Celsius, something like that. So we were not burning people. So now that brings us to objective 2. And it says in here, we're going to state the specific heat values of water and air. So listen, the introduction to heat, it says energy is the ability to do work, and it comes in many forms: electrical, mechanical, sound, atomic, solar, and of course, heat energy. And we describe energies in kilojoules for heat energy, kilojoules, or British thermal units. Okay. And these basically mean the same. Now, one is metric and one is imperial. So here is the definition of a BTU. It is a unit of energy, and it is 1 BTU is the amount of heat required to change 1 pound of water by 1 degree Fahrenheit. That is the definition of a British thermal unit. And the metric equivalent to the BTU, we use kilojoules, and it's the amount of temperature to raise 1 kilogram of water by 1 degree Celsius. And it takes 4.2 kilojoules to do this. This is 1 BTU. This is 4.2 kilojoules. So there's a difference in there that you need to be concerned about. But that's the definition of a BTU. Does anybody know how many BTUs a boiler horsepower is?
33,475.
It is 33,475 BTUs is a boiler horsepower. Okay, 33,475 BTUs is 1 boiler horsepower. Now, our appliances, gas burning appliances most specifically, are rated or given an input value in typically BTUs per hour is usually what an appliance is usually inputted at, or the input rating. Sometimes they're rated in kilojoules per hour or watts, right? So we have appliances, gas burning appliances usually have an input rating, and it tells us how many BTUs per hour that they burn fuel, okay? So that will come into play at some point in our future. Sensible heat, which is really important. Sensible heat is the heat that causes a change in temperature only, not in state. It is how much heat is required to change the temperature. Now, in our in what we have to do, we have to calculate sensible heat, and we will use a formula. And this formula starts off by saying the heat And the heat is measured in BTUs or kilojoules. And we are also going to take the mass of the substance that we want to heat up. And the mass is always in pounds, LBS, or in kilograms. So our mass in this formula always has to be in pounds, or it always has to be in kilograms in this formula. And then in this formula, we're also going to have a delta T. And the delta T is for the temperature change. And our third variable for this formula is called specific heat capacity. And this specific heat capacity here is our multiplier. So these are given numbers. This specific heat capacity is a given number for whatever substance that we're using. And here in this spot right here gives us the definition of specific heat capacity. And it is down here. So the specific heat capacity of a substance is the quantity of heat required to change the temperature of 1 unit of mass by 1 degree. It is not indicative of metric or imperial, but there is metric and imperial numbers. So it means that it takes 1 BTU right here to change the temperature of 1 pound of water by 1 degree Fahrenheit. So this is our multiplier for water. And the metric equivalent is 4.2 kilojoules per kilogram per degree Celsius. So the specific heat capacities in this formula right here are given numbers, and I'm going to call those a multiplier. And that should bring us to a table of specific heat capacities. And here is the table of our specific heat capacities. So if we're talking about water as our substance, our numbers for a specific heat capacity is 1 BTU per pound per degree Fahrenheit. Or if we're talking about metric, it is 4.2 kilojoules per kilogram per degree Celsius. Now, if we're talking about ice as our substance, it is 0.5 BTUs per pound per degree Fahrenheit, or metrically 2 kilojoules per kilogram per degree Celsius. Steam just happens to be the same numbers as ice. Air has a specific heat capacity of 0.24 or 101. And there we have propane liquid has a specific heat capacity of that. So what I'm going to do is we're going to do some examples here. So we need our formula where the heat is equal to the mass times the delta T times the specific heat capacity. And I'm going to give you some examples. So how much heat is required to heat 50 pounds of water from 45 degrees Fahrenheit to 140 degrees Fahrenheit. So using our formula triangle, we take our mass, and the mass is equal to 50 pounds. We need our delta T. Our delta T is 45 to 140. So our delta T is 95 degrees Fahrenheit. We are talking about water. So our specific heat capacity is, let's look up here, right here.
Sorry,
It's
where did you get the
1.
95?
It's the temperature difference between 45 and 140.
Ah, okay.
So our specific heat capacity is 1 BTU per pound per degree Fahrenheit. So these are our variables, and we multiply these. So I go 50 pounds, multiply that by 95 degrees Fahrenheit, multiply that by 1 BTU per pound per degree Fahrenheit. Now, when we do this equation, the pounds cancel out, the degree Fahrenheit get canceled out. I'm left with BTUs of heat. So 50 times 95 times 1. It takes 4,750 BTUs to raise the temperature of that water from 45 to 140. So that's how we calculate BTUs. Let's do another example. Okay, how much heat is required to raise the temperature of 500 cubic meters of water? This is a swimming pool. From 50 degrees Fahrenheit to, oh no, Celsius, sorry, 50 degrees Celsius to 80 degrees Celsius. How much heat does it take? So I will just put this, I'm going to shrink this a little bit and I'll do the equation over here. So we have our formula triangle. It says take your mass. So wait a second, I have 500 cubic meters. Is that a mass? That is not a mass. That is a volume. So I have to get a mass out of this volume. 500 cubic meters. I know that there is 1,000 kilograms of water in 1 cubic meter. So my mass is 500,000 kilograms. So my delta T, I said we're going from 50 to 80. My delta T is 30 degrees Celsius. And the specific heat capacity, we're talking about water, but it's metric. So that's going to be 4.2 kilojoules per kilogram per degree Celsius. And now I could put all of my variables in. So that's 500,000 kilograms multiplied by my delta T, which is 30 degrees Celsius. Multiply that by my specific heat capacity of water, which is 4.2 kilojoules per kilogram per degree Celsius. And if I type this out, it's going to be a big number, isn't it? It's like some people have it here.
63 million? No. What did I do wrong?
It's going to be 33,081,450 kilojoules to heat that swimming pool water from 50 to 80. That is a lot of kilojoules.
Doug, I got the 63 million.
Oh,
That's what I
wait.
got to.
Okay, I was just going by what somebody wrote on there. Hang on. That's right. This number is wrong. Okay, so the right answer is 6, 3, and there's a whole lot of zeros. 1, 2, 3, 4, 6, 7, 2, 3, 4, 5, 6, 7 kilojoules. Okay, that's a little bit more, right? That's 630 million. Is that right? Is that what you guys got?
Only 6 zeros.
63
Oh, I have too many
million.
zeros. So it's 63 million.
Yes, sir.
Awesome. 63 million kilojoules to heat up that water, which is really a whole lot more.
Hey Doug,
Yes,
when
sir.
I did this, I just converted my 1 meter cubed into 2,205.43 pounds. And
Oh,
then my answer with the 33081450.
okay. Let me just hold on a second there. You can't, I don't want you to convert anything into pounds or anything into Fahrenheit, etc. If the question is in metric, we're going to keep it in metric. If the question is imperial measurement, we're going to keep it in imperial measurement. We're not going to swap back and forth. Okay.
Oh, I thought you just wanted BTUs for it.
No, well, this is the heat. I'm asking for how much heat. And the heat, when we're doing metric, is measured in kilojoules.
Okay.
Okay.
Will we never have a question when it's like in metric and then the final answer has to be imperial?
Never, never. Yeah. Connor, how many Toronto Maple Leaf jerseys do you have?
This is
Awesome.
an old one. This is Kessel.
Okay. Oh, little fat Kessel.
Yeah, but he makes it work.
Yeah. Okay. So we're going to do a bunch more examples on sensible heat when we get back from the break. So take 15 minutes, come back, and we will continue on with this lesson. Okay, 15 minutes. We'll see you at 10 o'clock.
Hey Doug, what was the password for your D2L to get on the site? Mine was already synced to my computer. I'm just trying to get a second screen going here.
Day, month, year.
Day, month, year? Okay.
Okay, everybody, welcome back. Get over there. All right. I am going to share my screen again. We'll do a couple more examples of this stuff, okay? So we can get a better understanding of how it actually reflects to us a little bit more.
Number one champion sound.
Okay, so here is the question. Can everybody see that question clearly? It's how much time, I'm looking for time, is required to heat a brand new hot water tank from 50 degrees Fahrenheit to 140 degrees Fahrenheit. The tank is 33 US gallons, has an input of 36,000 BTUs per hour. So this is the kind of tank that you're going to replace at grandma's house. So you go to grandma's house and you're replacing her hot water tank for her. Now, she wants to know how long it's going to take until she can have a bath after you finish installing this tank. And through these sensible heat equation, we can actually figure out how much time it will take for us or for you to then bath grandma. I mean, hopefully you're not bathing grandma, but listen, if you're a caregiver out there, bless you. Caregivers are super important, especially in this pandemic world. So if you're not a caregiver, well then start caring about somebody. Anyways, so this question, we're going to start off with our formula triangle, right? Where the heat, and the heat is in BTUs, is equal to the mass times the delta T times the specific heat capacity of the substance that we're using. And this is a hot water tank, so our substance is going to be water. So first off, we have to get our mass. Our mass, it says in here that we have a 33 US gallon tank. So that's 33 US gallons. That is not a mass in pounds or kilograms, so we're going to have to convert that to pounds. How many pounds in 1 US gallon? Shout it out if you know it.
7.5.
Nope.
6.24.
Nope.
8.33.
8.33 pounds in 1 gallon US. So our mass of water is 33 times 8.33. So we have a mass of 274.89 pounds is what our mass is equal to. Then we need to know what our delta T is. Our delta T is 90 degrees Fahrenheit. Our delta T is 90 degrees Fahrenheit. And now our specific heat capacity is water. So it's 1 BTU per pound per degree Fahrenheit. And now I could just plunk all of my numbers into my formula. 274.89 pounds, multiply by 90 degrees Fahrenheit, multiply that by 1 BTU per pound per degree Fahrenheit. So how much heat does it take to raise the temperature of this water? So it takes 24,740 BTUs, and you know what BTUs to heat this water. Now, I'm asking for the time it takes. So I'm going to go 24,740 BTUs, and I'm going to divide this by 36,000 BTUs per hour. And when I divide this out, the BTUs will get canceled out, and I will be left with hours. And I have 0.68 hours. And if I multiply that by 60 minutes in an hour, that's going to be 41.23 minutes it takes for that tank to heat up. And so you could say, Grandma, in 45 minutes, I can give you your bath. If you are that caretaker. Okay. So that's a real world application for sensible heat.
I got 40.8.
Well, I don't know. I just typed it on my calculator. I don't know. You could bath Grandma a little bit earlier than me, I guess. It's going to be pretty close. 40 minutes, 41 minutes. All right, all right. Any questions? Pretty straightforward stuff. Do you want to do another example?
Yeah, if we could, that'd be good.
One more example, sure. Let me just, I'm good. Oh, I'll leave that there for just a half a second so you can write it down. Okay. I will do another question here. Okay, there's the question. How much heat does it take to raise the temperature of 30 kilograms of ice at -48 to 0? So we'll use our formula triangle, where the heat is equal to the mass times the delta T times specific heat capacity. Our mass is 30 kilograms. Our delta T is 48 degrees C. Our specific heat capacity, now this is for ice in metric, is 2 kilojoules per kilogram per degree Celsius. If you go back to that table. And now I will put my variables in my equation. So 30 kilograms multiplied by 48 degrees C multiplied by 2 kilojoules per kilogram per degree Celsius. Takes 2,880 kilojoules. Yeah, thanks, Jess.
I'm addicted to finessing.
So that's not too bad, eh? Has everybody got sensible heat down? Sensible heat, remember, sensible heat is only for change in temperature only. Okay? And we could change the temperature of ice. We could change the temperature of water. We could change the temperature of steam. We could just get it hotter. We're not changing any state. So as we move on, we're going to come out to objective 3, where we actually change the state of this substance. So latent heat, by definition, let me just zoom in a little bit on this one here, is the heat that causes a change of state, not temperature. So change of state, we know that we can go from a solid to a liquid. And we can go from a liquid to a gas. Those are the change of states that we need to be concerned about. And when you add this so-called latent heat, it excites the molecules enough that they actually change state, right? So it's a certain amount of heat. It's a given number, and for these changes of state. And as we go down, we talk about what those terminology of changing of state is. So this is a solid, liquid, and a gas. So when we want to change a solid to a liquid, we call it the latent heat of fusion. If we want to go from a liquid to a solid, we call it latent heat of solidification. If we're going from a liquid to a gas, we call it latent heat of vaporization. And then when we call it a gas to a liquid, we call it latent heat of condensation. So this fusion is ice to water. This solidification is water to ice. This, a liquid to a gas, is water to steam.
What if I do this?
And that could be propane liquid to propane gas as well. Depends on that. And then from condensation, it is typically from steam to water. And these are the most prevalent that we're going to talk about. Now, in here, the latent heat says if you use 970 BTUs to change a pound of water to steam, you could also recover that 970 BTUs when you change the steam back to water. And this is the basic premise of a steam boiler. So we're going to give you some variables on here and a new formula triangle. So this table are latent heat values, and it asks you to memorize these. And I'm going to give you a new formula triangle, and here it is. And we're going to call it for latent heat. And we want to calculate the heat. And remember, the heat is either in BTUs or kilojoules. That's how we measure it. And then we're going to take the mass of the substance we're using, and we're going to multiply it by the latent heat value. So this is the formula for latent heat. For example, you can see if I'm going from ice to water, it takes 144 BTUs per pound of ice to change it to water. The metric equivalent to that is 335 kilojoules per kilogram of ice. The next one I want you to focus on is, for now, is just the water to steam. It takes 970 BTUs per pound of water to change it to steam. And the metric equivalent to that is 2,257 kilojoules per kilogram. So these latent heat values go here in our equation. So these numbers will go here in our latent heat value equation. For example, oh, that should be a question mark. Okay, how much heat does it take to melt 30 cubic meters of ice? Now, as you notice in this question, there's no temperature. I'm not counting on temperature at all. We're just melting this ice. So this ice is at 0 degrees Celsius. And when we melt it, it's going to be water at 0 degrees Celsius. There is no temperature change. This is at 0 and 0. So first off, we need a mass. Our mass is always in kilograms. or pounds. We have 30 cubic meters of ice, so we have to multiply that by 1,000 kilograms per cubic meter to get us a mass of 30,000 kilograms. Now, our formula says we're going to take our mass and times it by the latent heat value, and it's going to equal our heat. So we take the mass, and we're going to multiply by the latent heat value from ice to water in metric, which is 335. So it's 335 kilojoules to melt every kilogram of this ice. And that comes out to a nice ginormous number. Two, three, 1, 2, 3. That's 10,050,000 beat or kilojoules to melt that ice. Oops. Okay, let's do one more example. So how much heat is required to change 10 pounds of water to steam? So anytime you see an imperial measurement, you know you have to use the imperial latent heat of vaporization. So the formula says take your mass, 10 pounds, and multiply that by the latent heat of vaporization, which is 970 BTUs per pound. It takes 9,700 BTUs to take that 10 pounds of water and put it to steam. To boil it to steam.
Doug, just a quick question.
Yeah.
So that's never changing the actual temperature.
Never, Dawson, never. There's no change in temperature when we're doing a latent heat calculation.
And on the previous page, it said you could recover those BTUs.
Well, if this was 10 pounds of steam and I do the latent heat of condensation, it means that I can get from 10 pounds of steam, I can get 9,700 BTUs of heat from it. So this is the basis of steam radiators. When you fill a radiator full of steam, say you have 10 pounds of steam in this rad, as it condenses, it will give off all its heat, right? At 970 BTUs per pound.
Okay, thanks.
Yeah. So in the next bunch of things in this ILM, it just talks about doing a bunch of exercises. So I'm going to do some with you. And this is where we're going to take these and combine them together. For example, How much heat does it take to raise the, well, let me just rephrase that. How much heat does it take? Oh, what's going on? How much heat does it take for 3 pounds of ice at minus 28 degrees Fahrenheit to steam at 300 degrees Fahrenheit? I want to know how much heat it takes to get us there. Now, there's a bunch of steps involved with this, and I'm going to go over all those steps with you. So the first thing I do is I give myself a line on my page, and it will indicate my temperatures. So I'm starting off at the bottom at minus 28 degrees Fahrenheit. And on the imperial scale, I have to stop at 32 degrees Fahrenheit because there's a change of state that happens there. And then I got to go all the way up to 212 degrees Fahrenheit because I have to stop there because that's the boiling point and there's a change of state there. And then I go all the way up to 300 degrees Fahrenheit. So I first have to, oh, let me just get a different pen here. I have to raise the temperature of this ice to the freezing point. So I'm going to call this number 1. I'm raising the temperature of the ice. This is a sensible heat equation where we take the mass, 3 pounds, and we're going to multiply that by the delta T. So the delta T between these two numbers from minus 28 to 32 happens to be a 60-degree delta T. Times that by 60 degrees Fahrenheit, and we're going to multiply that by the specific heat capacity of ice in imperial measurement. If I go back to that table, it is 0.5 BTUs per pound per degree Fahrenheit. I'll just do some math here. So it takes 90 BTUs to raise the temperature of that ice to the melting point. And at this point right here, I need to change the state. I have this ice at 32 degrees Fahrenheit. I have to make it into water. So I have to add a certain amount of heat. I have to add the latent heat of fusion or solidification, where we take our mass and we're going to multiply it by that latent heat value, which is 144 BTUs per pound. If I go back to that table, that's the latent heat of fusion and solidification. And that will give me 432 BTUs. So now I have water at 32 degrees Fahrenheit. And now I'm going to have to raise the temperature of that water to the boiling point. So this was a latent heat, and now I have to go sensible heat. I'm raising the temperature of the water. I'm going to call this number 3. And it's a sensible heat equation where it says take your mass times it by your delta T. The delta T between these two numbers is 180 degrees. That's okay, Tyler. The 0.5 is the specific heat capacity of ice. Yes, it is the multiplier. So if I had my formula triangle for sensible heat, the heat is equal to the mass times the delta T times that specific heat capacity. And that's what that is. Latent heat is the heat mass latent heat value. Okay, so we're at number 3 here. We're raising the temperature of that water from 32 to the boiling point at 180. And then I multiply that by the specific heat capacity of water, which is 1 BTU per pound per degree Fahrenheit. And that equals 540 BTUs. And that is now I have water at 212. So now I got to change the state of that water to steam. And so I'm going to add latent heat to this water to change to steam. And the latent heat formula would say, take your mass and multiply it by the latent heat of vaporization, which is 970 BTUs per pound. Now that equals 2,910 BTUs to change the state of this water to steam. And now I have steam at 212. I'm going to raise the temperature of that steam to 300 degrees. So I'm going to call this number 5, step 5, where this is a sensible heat. So this is, again, sensible, latent, and this is sensible. I am going to raise the temperature of that steam from 212 to 300. That is an 88 degree delta T. So it says, take your mass for sensible heat, multiply it by the delta T, and multiply that by the specific heat capacity of steam, which is 0.5 BTUs per pound per degree Fahrenheit. And that comes out to 132 BTUs. Now, the final step is to add all of these heats together to get my total heat.
Sorry, the 970 in the part 4, is that, what is that? That's latent heat.
That's
of
the
water and
latent
steam.
heat. Yeah. Latent heat of vaporization condensation. It's changing water to steam. And Connor, you are right. It is 4,104 BTUs total is the total heat to take 3 pounds of ice at minus 28 to steam at 300.
So it's like the first part, the second part, third part, and fourth part. You're just finding what temperature it is to go up to that state and then what state of change that is.
Yeah, it's a sensible heat to raise the temperature to either the freezing point or the boiling point. That's sensible. And then latent to change the state, and then sensible again to raise the temperature. Correct.
Okay, that makes sense.
Let's do another example doing metric. Okay.
Sorry, you're just adding all those up.
Yeah, we added all these up, the ones that are underlined here, 132, 2910, 540, 432, and 90. We add those heats up to get a total heat. Correct.
So you always have to do it in those steps to get that answer.
Pretty much, yes. Yes. So let's do another example like this, but in metric. Are you ready? Can I move this yet? Is everybody there? I'm going to take your silence as yes. Okay. Oh, I spelled steam wrong. Okay, there's our question. Let me just see if I can move this over here. Oh, no, bigger. There's our question. How much heat does it take to raise the temperature of 50 kilograms of ice from minus 18 Celsius to steam at 250 degrees Celsius? So again, the first thing I do is I draw a line on my page and I put my temperatures on there. So we have minus 18 degrees C. And then we have to kind of stop right here at the freezing point. So that's why I write that down so we know. Then I have to stop at the boiling point because I got to change a state there as well. And then I go all the way to 250 degrees C. So the first thing I got to do is I got to raise the temperature of this ice to the melting point. So there is an 18-degree delta T here. So sensible heat would say the heat is equal to the mass times the delta T times that specific heat capacity. So we're going to take our mass, 50 kilograms. We're going to multiply it by the delta T, which is 18 degrees C. We're going to multiply that by the specific heat capacity of ice in metric, which if you go back to the table, it is 2 kilojoules per kilogram per degree Celsius. So it takes 1800 kilojoules to raise the temperature of that ice to the freezing point. And now I'm right here. I'm at the melting or freezing point, and I, at this point, have to add latent heat to this to convert it. So the heat is equal to the mass times the latent heat value. So I want to change this to water. So it says take your mass and multiply it by the latent heat of fusion solidification in metric, which is 335. kilojoules per kilogram.
Okay, how did you figure that out?
There is a table on latent heat values. So this is my latent heat value here. This is the latent heat value, which is here. And if we go back to the table, the latent heat of fusion solidification is right over here. Whoop, right here. And you can see it is 335 kilojoules per kilogram. So that's where I get that number from. Does that answer your question? Hope.
Yes, sir.
Okay, so we will multiply that out, 50 times 335. And that is going to equal, let me write this down in black, 16750 kilojoules to change the state of that ice.
That's
Now,
called fusion. Sorry, Doug.
that's the latent heat of fusion solidification,
Okay.
either or. Now that I have water at 0 degrees, I have to raise the temperature of that water. And I'm going to call this number 3 because we're just raising the temperature. This is a sensible heat equation. And I have 100-degree delta T. So sensible heat would say, take your mass, multiply that by the delta T, multiply that by the specific heat capacity of water in metric is 4.2 kilojoules per kilogram per degree Celsius. And that should equal 21,000 kilojoules to raise the temperature of that water from 0 to 100. Now, which brings me to number 4. Right here, I have water at 100 degrees C. I want to change the state of that water to steam. That's a latent heat equation where it says take your mass and multiply that. This is going to be the latent heat of vaporization condensation in metric of water, which is 2,257 kilojoules per kilogram. And that is 112,850 kilojoules. And now that we've got that water to steam, I want to raise the temperature of that steam. We call this number 5 to 250 degrees from 100. So that's 150 degree C delta T. This is sensible heat. So it says take your mass. Multiply that by the delta T, which is 150 degrees C. Multiply that by the specific heat capacity of ice, or excuse me, of steam in metric, which is 2 kilojoules per kilogram per degree Celsius. And that equals 15,000 kilojoules. Why am I putting BTUs there? 15,000 kilojoules. And now the very last step is to add them all together, add these heats all together to get total heat. 1,674 kilojoules.